continue with our presentations this afternoon. There are two more presentations left in this session on fuels and reductants. Following that, we will move to a panel discussion to close things out. So, my penultimate presentation is going to be delivered by Dr. Huang, who is a leader in the blast furnace group at China Steel Corporation in Taiwan. And the presentation is going to be on the topic of progress in low-carbon blast furnace initiatives at China Steel Corporation, which I think, given our discussions this morning around the fact the blast furnace will be around and is going to stay around, will be, I think, an interesting presentation. So, Dr. TSUNG-YEN, where are you? Yes, there. I haven't got my glasses on. I see you now. Please come up and deliver your presentation.
Thanks, Andrew's introduction. Good afternoon. Please allow me to introduce myself again. I am Huang from CSC Taiwan. Firstly, I would like to thank worldsteel for giving us this opportunity to report our decarbonization progress on the blast furnace. Firstly, I would like to brief our company CSC, then talk about our commitment and the countermeasures for carbon reduction. After that, I will share our experience and the trial result on the HBI charging and the 1-2-year hydrogen, COG and the natural gas injection test. Finally, give a summary. CSC Group is the only one integrated large steel mill in Taiwan. Our annual hot metal output is 15 million tons, produced by 6 blast furnaces and 1 EAF. The production process includes from the raw materials to the blast furnace iron making, to the BOF steel making, and all the way to the product. Our iron making is mainly based on the blast furnace, so sure, it's consumed about 75% energy, and it's according carbon dioxide. This figure shows our commitment and the pathway of our decarbonization countermeasures. At this moment, our commitment is 7% reduction on the basis year of 2018 CO2 emission. We do try our best to optimize the energy efficiency and use the renewable energy. So we are confident that we can achieve the commitment of this year. And for the next stage, our commitment is 25% reduction by the 2030s. Firstly, we will charge the low carbon ferrous material into the furnace, and then we will use the hydrogen contained gas to replace part of the coal to inject into the furnace. The third one is that we will collect our process of gas and provide this gas to our neighbors. Our neighbors are the petrochemical company. They can convert our off-gas into a chemical product. The last one is that we will increase the addition amount of the scrap in the BOF process. Among these 4 countermeasures, we will take the way which are more economically feasible into our daily operation. For further in the future, we will see if the green hydrogen and the green electricity are available and in a reasonable cost. We will consider the route of the DRI to the EAF or DRI to the smelter. Okay, this figure shows our route toward the low carbon blast furnace. Firstly, we will charge in the low carbon material into the furnace, we do regularly charge the reduced ion to the furnace, and we have a short time period test on the HBI and the high ratio pellet. For a hydrogen content gas, we erect a 1-2-year injection equipment for testing the COG and the natural gas. Later, I will talk more about the HBI charging and the 1-2-year injection. For the top gas, we have built a pilot plant to capture the CO2. In addition, we collaborate with academic professors and research center to study how do we reuse the top gas after CO2 separation. Okay, for now, I would like to share our development and the trial result on HBI. As we know, the size and the density of HBI is much higher than the regular ferrous. The length of HBI is about 120 millimeter, and the mean size of lump ore and the sinter ore is about 22. A pellet is about 10. So to ensure the HBI can be safely conveyed to the top silo and can be smoothly to discharged out of the silo, and most importantly, the HBI can be precisely to discharged to the target position of the top furnace. We carry out a real-scale particle flow and movement simulation. Before running the simulation, we calibrated the physical properties of the digital particles by our own experimental result, such as repose angle, static friction coefficient, bulk density, and the restitution. So these are our real experimental. So we are confident that the digital particle model is very close to the actual behavior. Our simulation is from the materials on the conveyor belt and then filling into the top silo and discharge out of the silo, and finally distribute to the top furnace. These simulations are all in a real scale geometry. So the HBI is in the original size and is delivered by the conveyor belt to the top silo. In this simulation case, we use the 150 kilogram HBI to replace the sinter ore. And we run this simulation by NVIDIA DGX computer, which is equipped with 4-piece 8100 GPU. So the total particle number can be over 60 million. So in my point of view, this simulation is really vividly. And this simulation result were validated not only by the top furnace profile meter, but also a 1/12 scale experimental top furnace model. So totally, we distribute 6 layers burden on the top furnace. During the ferrous charging, we observe that the coke was pushed to the center area. And to analyze the material distribution and its characteristic, we divide the top furnace into 10 equal rings. And we found that the HBI dispersed uniformly from the wall area, here's wall area, to the center, and this color is HBI. And we also found that amount of HBI at the center is slightly higher than in the wall area. This figure shows the ore to coke ratio and the porosity profile. We can see the ore ratio at the wall area is high, and the porosity at the center is the highest, and the wall area is also quite good. Our production engineer is very happy for this distribution. Followed are our trial result, operating result. The HBI charging rate is from 50 kilogram step by steply increased to the 180 kilogram per tons of hot metal. During the HBI charging, the lowest coke rate was 280 kilograms per tons of hot metal. And we operate the calculated theoretical flame temperature and SPPV at the lower level. It is because we want to keep our hot metal production rate same as our base case. So we saw the permeability is quite good throughout the HBI period. And as we know, the HBI is mainly consists the metallic ion, so it requires less reduction. The total oxygen demand is decreased from 230 to 205. And also, the burden descent was quite stable, no slip, no drop occur. This figure shows our HBI decarbonization performance. The lowest carbon reduction rate is 419 at the 180 kilogram HBI addition. And with increasing the HBI rate, the CO2 reduction rate decreased accordingly. And after we consider the in-plane energy balance, such as top gas, heat, and utility usage, the average reduction rate is at 1.5 tons of CO2 per tons of HBI addition. Then I will share about our 1-2-year injection test. So far, we CSC operate all of our blast furnace with PC injection, have no experience with gas injection. So to firmly develop hydrogen-rich gas injection technology, we prepare a 1-2-year gas injection system. The first objective is to define the safety control sequence for gas injection and further to evaluate the combustion characteristic of the natural gas and the COG. We have two individual injection lines, natural gas and COG. The natural gas pressure in our supply network is 6.3 kilogram per centimeter square. Our hot blast pressure is about 3 to 4. So the natural gas pressure is enough to directly inject into the furnace. On the other hand, the COG pressure is at the atmosphere. So we need use a compressor to boost the COG pressure to about 8 bars. In addition, the COG contains tar. After long time operation, the tar will deposit inside the pipe. So we will use the steam to wash the tar. This picture shows our compressor. That is a reciprocating type. The maximum flow rate is 800 normal cubic meter per hour. And the footprint is about 6 meters plus 3 meters. That is a two-stage compression. The first stage is compressed to 1.5 bar, and the second stage is compressed to 8 bar. If the outlet pressure does not reach our set point, there is a recirculation valve, and the valve will gradually open to recirculate the partial compressed gas into the first stage until the outlet pressure meet the target. This picture shows our gas valve station and natural gas line here and the COG line here. And at the entrance, there is a gas pressure gauge here, and outlet pressure have a pressure gauge. Through the pressure difference between the entrance and the outlet pressure, we can understand if right now if a gas leakage inside the gas station, and we use the outlet pressure to decide if right now it's under the normal injection or have to stop the fuel gas. In case if the abnormal situation happened, these two valves will automatically close and open this vent valve. The most importantly, we have a high pressure nitrogen. This is the failure open and immediately open, and the nitrogen will flush the pipe all the way to the furnace. For the injection method, we individually test the length injection and the 42-year injection. This slide is to compare the raceway dynamic between the lens and the posterior injection. Here we set a back cover camera to observe the raceway behavior. The upper row is the lens injection video, and the lower row are the 2-year port injection. During the experiment, I closed the PC, and the first column is just only a small amount nitrogen flush the pipe. We can see the brightness is the highest compared to the fuel gas case. And then when we increase the injection rate from 200 to 600, the combusted luminous intensity fade gradually. And when we compare these two methods, the lens injection shows significant reduction in the luminous intensity. On the other hand, gas port injection does not. So we suggest that the 2-year port injection offers better combustion performance because of the good mixing between natural gas and the hot air. This slide shows our simulation result, CFD simulation result. According to the real geometry, the outlet position of the lens is here, and the posterior outlet position is here. It's more toward to the raceway. So the ignition point is at the raceway. On the other hand, the ignition point of the lens injection is inside the 2-year. So the pressure drop at the 2-year is 0.388 atm, much higher than 2-year port injection. So this is not good for PF operation. And also, I would like to compare the raceway behavior between natural gas and the COG. So here shows the COG and the natural gas composition. COG is directly with hydrogen, 56%, and methane, 25%. And natural gas has many methane, 92%. Hydrogen can be directly combusted, but methane cannot. And I also noticed that if I count the total hydrogen atom, natural gas is with higher hydrogen atom than the COG. So currently, COG and the natural gas are available hydrogen content gas we have. And so far, I still do not know which one will not impact our normal operation too much. So I respectively inject the natural gas and the COG at the same flow rate to compare their raceway behavior. This figure shows my experimental procedure. Firstly, I stop the PC and switch to the COG injection 300 and increase to the 600 and turn off for a while, just only breast and switch to natural gas 300, 600 and go to our normal operation. Again, I would like to observe the raceway behavior by the back cover camera. This video shows the hot breast-only video, the highest brightness. That is because the caused by the heat radiation from the cold combustion at the raceway. And in addition, the calculated theoretical flame temperature is the highest, 2,400 degrees higher than the fuel gas injection case. As the injection rate increased to the 600, the raceway gradually becomes darker, especially at the outlet position of the gas port, likely due to the cooling effect by the room temperature injectant. At the equal injection rate, COG shows higher brightness than the natural gas. I believe that the hydrogen and the carbon monoxide content, COG, can be combusted directly with hot breast in a very short time. And the natural gas with methane require endothermic cracking before burning. During my experiment, there are only indicated data I can collect. There is breast rate and the 2-year heat loss at the test 2-year. This 2 chain shows here. We can see after COG injection, the hot breast drop and go back to the normal as the COG stop, and then breast rate keep decreasing during the natural gas injection. This behavior suggests that the injection gas combusts very very soon inside the tube ear here. And the combustion gas volume expands sharply and creating the additional flow resistance at the tube ear outlet and reducing the blast rate. I average each step data into this figure. We can see the CO2 injection has lower blast rate than the natural gas injection. And we propose the CO2 provide good combustibility and generate larger combustion gas volume. The red color chain shows the heat loss. Here is a water jacket. Heat loss means that how much heat is taken away by the cooling water. And if the heat loss decreases, means that the gas temperature inside the tube ear is lowered. So we can see with CO2 injection, no significant changes. And with natural gas injection, heat loss goes down. This suggests that natural gas does not combust effectively and instead cooling down the surrounding hot air. Finally, give a summary. Under the decarbon pressure, CSC has planned the strategy to cut the emission in the medium term and in the future for the neutrality. We have developed the technology for charging low carbon raw materials such as HBI, reduced ion, and the pellet, and achieve a comparable result. And in addition, a 1-2-year injection test was conducted to validate the safety control sequence, and we will erect a demonstration plan for all 2-year injection to validate how effective at reducing CO2. When we decide whether we implement the decarbon measures, we need to consider not only just how effective they are, but also how much they may rise our operation cost. Thank you.
Thank you very much. Do we have any questions from the floor on the presentation? Thomas, you have a...
No question, only one remark. We operate in Linz now for 25 years, a coke oven gas injection and a natural gas injection in the blast furnace. It works very well and it can reduce the CO2 emissions. So we started this project 25 years ago and it's running very well.
Thank you. I think Ternium do something similar in their plant in Argentina as well. So hopefully you're set up for success. Any other questions? I don't... Nope. So, all right. Thank you. Oh, I'm sorry. I didn't see you behind Rizwan. Can we get a microphone here?
You have started experimenting this using of hydrogen in your blast furnace and through 2-year injection. And what is the capacity of your blast furnace right now? Is it applicable to the mini furnaces also?
This blast furnace in the volume is 2,900 square meter.
Meter cube.
Cubic meter.
Cubic meter. 2,000.
2,900 something.
Okay, thank you.
One more. I can see a question. I see a hand at the back.
Yeah, I am Joe from POSCO. Thank you very much. Very interesting presentation. I'm interested in the injection of COG. As you know well, natural gas is a clean gas, but COG has a lot of tar. Did you have any trouble to injection COG, or did you treatment or some to remove the tar?
Yes. For my experience, tar, CO2 contains tar, not only tar, but also many dust. So when the CO2 goes through the compressor, we have to have a filtration to screen the dust. Yes. After a period of operation, we also observe the tar deposit on the valve, shot of valve, and somewhere. Yes, I experienced these issues. Sorry.
Do we have a microphone?
Can we know what is the product PCF levels, product carbon footprints from your blast furnace route after implementing all these actions? So what is the level of carbon footprints?
Carbon footprint.
Yes.
Tons per ton.
Tons per ton.
That is just only 1-2 year injection, so they will not impact our furnace too much.
Okay.
So we cannot
Yes.
feel any difference on our normal operation.
Okay, thank you.
Thank you. Great presentation. Okay, our next and final presentation is going to be delivered in Mandarin. So if you don't speak Chinese and would like to hear, you will need to use your simultaneous translation device, which should allow us, or allow me, to understand the presentation, which will be delivered by Ms. Ban, who is a Deputy Director and Senior Political Officer at Baotou Iron and Steel, where she's in charge of the company's ecological design and green manufacturing, research and management. She's worked on many projects, on life cycle, on technology, but today is going to tell us about the carbon capture and storage demonstration project at Baotou, which I am certainly really interested in hearing about. So, Ms. Ban, the floor is yours. Thank you.
大家下午好，非常高兴世界钢协能提供一个这样的交流机会。我呢在这里先简单介绍一下我们公司的整体情况。包头钢铁集团公司是1954年成立，是新中国15期间的156个重点项目之一。经过70年的建设发展，已经形成了钢铁、稀土产业为主业，矿产资源综合利用、煤焦化工、物流、节能环保、装备及生产生活服务等产业新兴产业的一个协同发展的产业格局。是我国重要的矿产资源基地，拥有的白云鄂博矿山是一个集超大型铁、稀土、泥资源综合金属共伴生矿床，稀土储量居世界第1位，泥储量和土储量居世界第2位，并且富含萤石、抗、钾等多种国家战略资源。同时呢，包钢集团也是我国重要的钢铁工业基地，具备1720万吨的产能，拥有板管轨线4条精品线，可以生产高强钢轨、石油套管、汽车钢、家电钢、高钢级管线钢、高强结构钢等高端产品，也是我国的稀土工业基地，稀土选矿、冶炼分离、金属产能产量都居世界第1位。下面我就从3个部分介绍一下今天的内容。CCUS 是实现碳中和的重要路径。据 IPCC 和 IEA 指出，在预计2030年CCUS 达到4.9亿吨每年，到了2050年将达到46.6亿吨每年。同时呢，2021年我们成立的中国钢铁行业低碳工作推进委员会也提出了低碳发展6大技术路径。包钢也在这方面进行了布局，尤其是极致能效工程，以及呢建设了那个风电、光伏等绿色能源，并且呢也构建了用气风气电生产绿色氢气，在氢基速炉和电炉的这个格局，同时呢也及时开展了 CCUS 项目。 在碳中和的背景下，对于电力企业、钢铁企业、化工企业和水泥厂，从排放源中呢补给二氧化碳进行封存和利用，也是实现碳中和的重要路径。作为钢铁公司，主要包括化石能源的燃烧排放，以及溶剂的燃烧排放，包括那个自备电厂的二氧化碳排放。其中长流程炼铁二氧化碳的排放量能占到60%到70%左右。我们包钢的这个 CCUS 项目呢，主要是布局在了热风炉和石灰窑这里补给的。下面就简单介绍一下包钢的 CCUS 项目17。该项目是我们国内首个钢铁行业100万吨级 CCUS 碳中和循环示范项目。该项目目前呢，主要的电力结构是使用了常规的电网电以及风电和光伏电。运输方式呢，在厂内运输是建了管道运输。由于现在跟油田的合作呢不是太固定，所以呢原计划的是在企业跟油田之间也想建这个管道运输，但是现在油田的变化还是比较多的，所以目前我们还是在槽车运输。项目17我们是封存能力是50万吨，项目2期、3期建设后呢，每年的碳补给量就是200万吨。包钢的这个项目1期是2023年3月开工建设，2024年底完成建设，包括洗涤塔、吸收塔、再生塔等装备的安装以及厂房的建设。25年6月，项目1期成功实现了全流程的资源和那个全流程的贯通。随后呢，开始了查漏补缺，验证系统的稳定性与设备性能，进入了试生产阶段。10月份以来呢，进一步优化操作模式，探索工艺系统及设备运行的最佳参数，收集生产试验数据，核算生产成本，为钢铁行业 CCUS 项目积累经验。包钢呢，采用的是化学吸收法，对迈尔兹窑的燃烧后的烟气中的二氧化碳进行补给。补给的二氧化碳经过压缩，采用了槽车送至周边的油田。目前呢，我们迈尔兹窑的这个烟气浓度基本是在17%到20%之间。然后项目规模是1期就是每年产量是45.7万吨，其中气体的是4万吨，剩下的为液体。采用化学吸收法对低浓度的二氧化碳烟气补给，目前呢，该项技术已经非常成熟了。目前我们的产品浓度呢是完全可以达到4个9的，但是因为基本都是用在了工业上，所以呢，现在3个9就能满足下游用户的需求。这个项目目前最核心的点，主要是在这个吸收剂。目前这个吸收剂呢，是比传统的吸收剂，比传统的吸收剂呢，那个逃逸率低，并且呢，腐蚀性也小，能延长设备的使用年限。同时呢，它的这个吨二氧化碳的能耗呢，也比之前的说能降低24级焦，因为目前我们还没有就是满产，所以这个真正的这个能耗的数据还没有得到验证。下面我就说一下它的这个利用吧，这个应用场景。目前呢，项目呢，因为这个应用场景确实是存在很大问题，就是我们的补给能力呢，现在其实已经就是年产45.7万吨是没有问题的，但是我们下游的应用场景比较少。现在主要实现的就是地质封存，目前呢已经给油田供了一部分，也实现了这个注入，并且呢效果也比较好，但是量还是比较少， 并且我们的竞争力呢也没有这个化工企业的强，因为化工企业呢它的浓度很高，所以它的成本很低，所以我们钢铁企业的碳捕集没有优势。另一方面呢，我们是用在了这个包钢自己的一个碳化钢渣的这个项目里面。这个项目呢是通过综合处理钢铁渣，最终形成高纯碳酸钙和含铁料。其产品呢用于造纸、塑料、涂料和橡胶等多个行业。现在是消耗1吨钢渣呢，可以利用0.3吨左右的二氧化碳。目前因为是在厂区内2个项目，所以呢，我们从 CCUS 这个项目到这个高纯碳酸钙这个项目之间是实现了这个管道运输。另外呢，就是我们在多方面的探索这个捕集到的二氧化碳的应用场景。也是集团公司呢布局了用二氧化碳生产碳酸氢铵这个项目。也是为了延伸下游的产业链。该项目建成以后呢，预计每年可消耗11万吨二氧化碳。同时呢，我们也布局了用二氧化碳和这个气风气电生产的氯氢来生产甲醇项目，就是在多场景提供应用。同时和包钢呢也联合包头市农牧局开展了这个农业示范基地二氧化碳气肥的试验项目，按照1年2收测算，每亩农作物可吸收约2吨二氧化碳。就是包钢始终在研究应用各种拓展这个二氧化碳的利用途径，但是确实很少。我们在这个焊接的保护气体使用二氧化碳，包括转炉底吹二氧化碳，就是各种场景在用，但是呢量都很小。我们也是下一步也在积极的与各个研究院所在探讨，如何能更好的将捕集上来的二氧化碳进行利用。虽然包钢的这个二氧化碳这个项目呢已经建成了，但是从示范走向全面商业化和规模化，还有诸多的挑战。今后呢，我们也要不断的这个积累数据、验证技术、降低成本、解决难题，力争实现环境效益与经济效益同步提升。感谢聆听。
Thank you, Ms. Hua Ben. Do we have any questions? I wanted to ask, if I could, whether your capture technology, is it something that you developed yourself, or is it something you purchased from another supplier?
是我们跟一个叫百利时公司合作成立的公司，是该公司的技术，我们直接拿来应用的。
Thank you. And at the moment, the capture technology is on the lime kiln. You plan to also, I recall, put it on at the stoves at the blast furnace. Is that part of the plan at the moment?
对，我们现在目前是在这个麦尔兹窑上用的，也就是石灰窑上。然后呢，我们还布局在了那个高炉热风炉这边，会逐步拓展它的应用。因为布局了是200万吨的，现在是50万吨建成了，后续还有150万吨，所以会在高炉上应用。
Well, it's first of a kind technology, so I don't see any further questions, but congratulations and thank you very much for your presentation.
谢谢，谢谢。